So I will start today with explaining the properties of stress-strain curve. Some of you might know it, some of you might, this thing might be new to them. Let's start with simple rod like this, and I apply the tension force of a P, for example. What you gonna, so whoever just like came in, there is a, yeah, just to make sure that everyone know, under modules, topic 2, download lecture 2 for note taking, okay? I just don't want you to suffer and like start taking pictures on your phone and waste your time drawing and all this kind of stuff, okay? So let's start with having a simple rod like that, and I apply the tension. So this rod gonna expand or elongate like this. And this elongation, we call it delta, or we call it delta L. And delta L is simply L final minus L initial. So L final is this whole thing, which is the length after deformation, minus L, or we can call this L initial or L node, which indicate that this is the original length of the bar. So if I have something like this, a member, I elongated it, you have a delta. Similar to stress, we agreed last lecture that force doesn't indicate intensity. But when you divide it over area and tell me what the unit area feels, that indicates intensity. Similar to the elongation and deformation. If someone came to me and tell me, okay, I have a delta of 10 inches, and another one came to me and told me that I have a deformation of 1 inch, okay? I can't tell if the material is going to break or no, because for example, this plastic tube, if I elongate it much, it can break. We don't want that to happen in building. We don't want this steel bar, for example, when you elongate it, we don't want that to break in the real structure. That's why we want to know what's our limit. And the limit for those is not, it can be detected by only deformation. It is incomplete sentence. So instead, you should tell me, okay, it elongated by 10 inch, but how long the member was. So, for example, if this member was originally 200 inch, so the ratio between the delta and the original length is, for example, 0.5% or 0.005. And the units here are going to be inch over inch, which is unitless. I'm just like getting the ratio of the deformation to the original length. What I'm trying to do here is I want to know the amount of deformation per unit length. So I'm dividing the delta, which is 10 inch, over 200 inch. What I want to find here is I want to find how much elongation the unit length had. So if I'm working with inches, now I know that every inch elongated by 0.005. This is something that I can build a judgment based on it. Because in the, for example, if you go and like buy this steel bars from any factory or like any workshop, they will tell you this thing gonna break at a strain equal 0.1. And strain is a ratio between the delta and the delta over the original length. Or in other words, the strain is the amount of deformation per unit length. So if you have an 0.1 strain, that's when your material gonna break, and you don't want that to happen. So in the first case, every unit length gonna elongate by 0.005. Is that safe or unsafe compared to the 0.1 here? It is safe, right? Because again, 0.1 here tells you if unit length elongated by 0.1, that's a red flag. That is gonna break. So the other guy who came to me and told me, okay, I have a delta of 1 inch. Again, can I build a judgment based on that? I can't. You need to tell me what was the original length of that member that elongated by 1 inch. If you told me that the original length of that was 10 inches, so now I know that the unit length or every inch elongated by 0.1. Is that safe or unsafe now? That's unsafe. So to have a good judgment about the deformation, you need to divide it by its original length so that you can find what each unit length elongated by. For example, in concrete, and that's like in the codes, the design codes, it tells you that the concrete is like we call it strain, is 0.03. So after which it's gonna break or crush. So what we did now is something we call strain. We divided the delta over the original length. And this is what we call strain. And strain here is we draw it like, or like we write it like this, an E, and you can have your own signature at the end. Don't make it like a straight E like this, or like capital E. That's like something else we're going to discuss now. But you want to have it in this curvy way. We call it epsilon. So what we did now, we call it normal strain. And at this point, I think if I said normal strain, you understand that this is a strain that happened due to a force that's either tension or compression, which is normal to the cross section or perpendicular to the cross section, which is either tension or compression, which will cause either elongation or shrinkage or like shortening. Okay? So the equation for that is epsilon, and you can have your own signature at the end, like this line. You can say delta over L naught, or you can say delta L over L naught, and you can either L naught or use L initial or L. But you understand that this L is the original length. What's the units here? Delta L or delta, they are either in inches or millimeter. Similar to L naught, so that you can cancel them with each other, inch or millimeter. And then the epsilon itself, the unit will be inch over inch or millimeter over millimeter, which will cancel each other and it will turn out to be unitless. But now once you understand the whole concept of this, a strain means the amount of deformation that the unit length have. So let me give you an example just to make sure that I can move to the next slide. If I have a member that's 100 inch long, and I told you the strain of that member is 0.5, it's going to strain by 0.5. What is delta? Without looking at the equation, just like remember the definition for the strain. It is the amount of deformation per unit length. So that you know that the unit inch going to deform by 0.5. 1 inch going to deform by 0.5. Now, what about 100 inch? How much is going to deform by? Anyone? So you can do something like this. So I know that 1 inch going to deform by 0.5. Okay? What about 100 inch? How much is going to deform by? And this is delta. And you can do this cross thing, which will turn out to be 100 times 0.5, which is same to this equation, though. This equation tells you a strain, which I can put here 0.5, which is the strain, equal delta, which is this is what I want, over L naught, which is 100 inch. So delta will be this two multiplied by each other, and it will turn out to be 50 inches. Is that clear? Tell me.
So for delta equals 10 inches over 200, the result is 0.05, not 0.005.
Oh, okay. My bad. So now this is safe or unsafe? It's still safe. Yeah, I mean, like, we are talking about steel now, not concrete, this one. Okay? Any questions? All good? Okay. Let's move to the next slide, which is, let's now define the strain. So the strain, we can say it's a deformation of a material from stress. Okay? And this deformation can be, you can say, you have two deformation. Either deformation is perpendicular to the cross section. If the deformation is perpendicular to the cross section, which is in terms of like tension or compression, this is what we call normal strain. Okay, it's easy to guess now. What about the other type of deformation? Anyone? Correct. So if you have a deformation that is parallel to the cross section, what we call it? Shear what? That's correct. And we're going to explain at the end of this lecture. So we either have normal strain or a strain that is parallel to the cross section. Normal strain or a strain that's parallel to the cross section, which is like gonna move in form of like a sway or anything like that. That's like a deformation. We call it shear strain. And we're gonna explain it in more details at the end of this lecture. And let's now define it. So normal strain, I want to say amount of deformation per unit length. Okay? So now let's derive, I'll have you all tell me the equation for the delta. So now, if I have the same piece of rod, and it was plastic and has a diameter, and I elongated it by force. So what do you think the delta, or like the deformation of that member when I pull it, gonna depend on? First thing, and you can start guessing. So if I have this thing, and I elongated it, this amount of elongation depends on what? Initial length, okay. So it depends on the length. What else? Force. What else? If I have a plastic and I have a steel, is it different?
What it's made of.
Material, that's correct. And last thing, anyone? You're right, but like this, now we are talking about delta due to force. Next lecture we will talk about delta due to temperature. But let me tell you something. If I have let me show you this. This might make more sense. Cross section. Yeah, do you agree with me? If I have this cross section, it's different than if I have like a bigger cross section. Like if I have a larger diameter, it's gonna be hard to deform, right? So the cross section also, I will say A, which is the cross section or area. Okay? So let's put it now in an equation form. Okay. If I increase the length, will the delta increase? I'm just like trying to make proportional. Yes. So I'm gonna put the L at the top, which if L increase, the delta gonna increase. What about the force? If the force increase, the delta gonna increase or no? Yes, so I'm gonna put it up. What about area? If I increase the area, the delta gonna increase or decrease? Decrease. What about material? If I use plastic and I use steel, I mean like if I increase the material, or like I use the better material, will the deformation increase or decrease? Decrease. So we want to put the material in a form of E, which is something we call, anyone? Correct. Modulus of elasticity. So what does modulus of elasticity means? Every material has its own modulus of elasticity. And this modulus of elasticity, or modulus of elasticity, or we call it Young's modulus, it measures the resistance of a material to non-permanent deformation. Okay? In other words, if I have a steel and I have a plastic, and I pull them like hard, this one, I'm not strong enough, but if I'm strong enough, I can pull it in a way that this thing gonna elongate. So now I have a permanent deformation, similar to the spring. So if I elongated the spring enough, sometimes it cannot return back, right? Similar to the steel, with the same force. If I apply the same force that elongated the spring on the steel, do you think it will have a permanent deformation? Do you think it's gonna elongate in my hand? Like this steel and spring, you know the spring, right? If I apply the same force on it, like if I apply the force on a spring that I caused a permanent deformation, and the same force I applied it here, do you think this steel gonna elongate with me? No. So that's what modulus of elasticity means, and there is a tables for this. So it is like a constant that measure the stiffness of the material, and you can find here that the steel is 200, for example, and it's of course stronger than the aluminum. Okay? So we use this modulus of elasticity, and like in this table, and you can find this table at the end of the booklet, you find the GPa, which is gigapascal, or MPSI. And MPSI here is mega PSI, or mega pound per inch square. And if I want to convert mega to PSI, I'll just multiply by 10 power 6. Okay? So now, modulus of elasticity, you can write that it measures the resistance of the material to non-permanent deformation. And you will find me a lot now talking about non-permanent deformation and making sure that when I elongate an element, I want to make sure that it returns back. And I will show you a video right now why it's important to not have a permanent deformation in our structures in a moment. But let me continue now. The units of the delta, so I have a length. It can be inch, it can be millimeter. Force, pounds, kips, newtons, kilonewtons. The area, you need to follow what the length was in units so that you can cancel them together, either inch square or millimeter square. And E is in a unit of stress, which is MPa, PSI, KSI, for example, or gigapascal. But you want to have your units in that equation and all the equation throughout this class consistent so that you're able to cancel the force with the forces or the length with the lengths. And the delta eventually will be in a unit of inches or millimeter. Okay? Any questions so far? You understand the whole equation where it came from, right? Does it make sense, like the equation? Okay. So now if I told you I want to make a relationship between P and delta, if I increase B, what will happen to delta? It's going to increase, right? It's directly proportional. But is that relation meaningful? So let's combine what we explained in the last lecture and what we explained now. Let's talk about P. Is P indicate anything? Yeah, P is the force. So if I want to make this force indicate intensity, what should I divide this force by? Area, to make it stress, right? So if I want to make a relationship, which is P over area here, and instead of using delta, and I want to make a meaningful parameter here, would I say delta, or what should I say? What should I divide this delta by? By the modulus. Or if I want to, okay, let me put it in a different way. So if I want to make this force indicate intensity, I will use it in a form of stress, which is I will say P over area. And if I want to make the deformation make sense, I want to divide it by the length so that I can get for example, the deformation per unit length. So that's more meaningful. So instead of using delta now, I will use a strain, which is delta over L. What I did here is just like divided by L, And here, what I did, I divided by area. So that I will end up in a relation which is P over area, which is a stress, and delta over L is the strain. Do you understand that P over delta, that's nice. Yeah, we all know it's direct relationship, but like it doesn't indicate like this relationship is missing a lot of things. When you see a relationship between P over delta, you might have a lot of questions, which is, what was the cross section that you built this curve on? Or what was the length of the member that you built this cross section on? So you have a lot of things that are missing that can't build your judgment. That's why we need to have this curve more meaningful. So we divide the force by area to have it in a stress so that we know what the unit area feels. And then we divide this delta by L to know how much deformation per unit length. So now we have everything. We have now a curve that is applicable for any length, for any cross section, for any force, for any delta. This is more general curve. Do you agree with me? Anyone? Thank you. So, of course, this curve is still missing, and we're gonna talk in a more details now about that. But let me show you a video of, I wanna now apply stress on this, or I wanna apply force on this rod, and I wanna find how it's gonna behave. So this video, you're gonna see it live tomorrow. You're gonna see it live tomorrow before the discussion. We will have a stress strain test, which is like the tradition of this class that you see this test. I just want you to see how this stress behave, how this rod behave when you apply stress. 1 minute. Okay, we are applying stress. You're gonna see now it's elongating, and the cross section, focus on this cross section, is gonna decrease. And it's also elongating. Do you see this decrease? Now you see it more. And this is what we call necking until it breaks. Okay? Let's draw the curve on what happened here. So, at the beginning, stress strain, it started like this. It started like a line. And this line means when we increase the stress, the strain gonna increase to a point what we call proportional limit. And proportional limit is the last point in a line where the curve gonna behave in a linear elastic. In other words, if I loaded this member until here and I unloaded, just focus here on if I loaded and I unloaded, it's gonna go back to 0. So I don't have any permanent strain in the rod. It's important. I loaded it, I decided to stop, I removed the loading from the machine, or the rod from the machine, there will be no any permanent deformation, which means that if I measure the length of it, it's gonna be the same. But not once, if I just added a little bit more stress here, it's gonna curve. And this is we call elastic limit. Okay? And the elastic limit also, if I loaded here, if I loaded the specimen and I stopped here, it will also gonna return back to its like original shape. So there is no permanent strain. But the thing is, what is the difference between proportional limit and elastic limit? That one of them is linear elastic and the other one is not linear elastic. I mean, like, it's not linear. So this region, this whole region, we call elastic region. and the material behave in an like elastic behavior. And what does that mean again? That means if you load it until plastic limit or elastic limit, they will, and you unload it, it's gonna return back like this to the zero. The thing is, what I need you to notice here, which is like the difference between the proportional limit and elastic limit, that this line, the linear elastic line, it does have a slope. Okay? And if you want to figure out this slope, I want to tell you first that you all agree with me that the stress is proportional with strain, which means if I increase the stress, the strain gonna increase, and the vice versa. So we can remove this relation, or like this proportion. I want to say there is a constant here. And this constant, ladies and gentlemen, is called modulus of elasticity, which what we explained before. So every material has its own modulus of elasticity. Every material has its own curve or like own relationship. And steel, for example, have a high E, so the slope is gonna be not that steep. It's gonna be like a little bit, like it's, okay, let me tell you what does the slope mean. If I have a material that has this kind of slope, what does that indicate? That indicates if I apply a stress here, the material gonna deform big time, and you don't want to happen. And instead, the steel, when I apply stress here, this is gonna be the deformation. If I apply, like, increase the stress a little bit, this is gonna be the deformation. This is like barely difference between them. But if you have a material that has lower E, it's gonna be something like that. So if I apply a stress here, for example, this is the deformation. And if I increase a little bit the stress, you see the difference in strain, like it deformed, and you don't want that to happen. Or like for us as a civil, we don't want that to happen. The difference between proportional limit and elastic limit now, that this relationship we call Hooke's law, and Hooke's law doesn't apply on elastic limit. It does apply only until the proportional limit, because it's like linear elastic. And once you passed the proportional limit, it's no longer linear. It's still elastic, but it's no longer linear. But it's still elastic, but it doesn't, it's like inapplicable to use the Hooke's law on it. So if I give you this relationship, for example, in the exam, or you see it in the site, and you want to figure out what is the modulus of elasticity of that material, what I want you to do is to pick any 2 points in the linear elastic. Don't go past the proportional limit. Don't, for example, tell me this is the stress, and over this strain, and I can get the modulus of elasticity. Because modulus of elasticity here, you can see, I can put it in another way. E is equal stress over strain. So if I have a value for stress, and I have a value for strain, and I divided them, I'll get a modulus of elasticity. But that's only valid in the linear elastic region. I don't want anyone to take anything beyond the proportional limit. And you will understand why now, right? It's all clear. Okay. What happens beyond the elastic limit? So beyond the elastic limit, so it still goes straight. This is the first region. Beyond that, I have something we call yield, which is the materials start to just like start to go up and down like that. And this up and down is a result of a breakdown in a material, like a molecule level, and that's when a permanent deformation gonna start to happen. If you unload any point beyond the elastic limit, you will have an permanent deformation. It's gonna be like this. It's gonna like go up and down a little bit like that, and then it's gonna go like this until here, for example, it fractures. Okay? Okay, let's talk about this. So if you have a curve like this and I want to find the yield strength is at the point where you have like this ups and downs. So this is your yield stress, okay? If you look at any brochures of a material or like the codes of design, you will not find proportional limit stress or like elastic limit stress. Instead, what you're gonna find is a yield stress. Any material is defined by its yield stress, not the proportional limit, nor the elastic limit. Although it's obvious to just classify the material based on a plastic limit, but it's so hard because at this point everything's happening quickly, and practically, it's controversial among researchers, for example. I'm not talking about myself, I didn't work in that field, but it's like controversial to which stress to take because like this happens so quickly. And instead, the yield strength, it's so obvious and well defined. So when we design our materials, we design it on the yield strength. But some of you might tell me, okay, there is like, if I design on the yield strength and the material went to the yield point, it's gonna have a permanent deformation. Yeah, this permanent deformation in metals like steel and aluminum is 0.2%. And that's like the definition, for example, for the yield strength, I will say a stress at which a predetermined amount of permanent deformation occurs. And the reason why we, again, choose the yield, because it's well defined and we can get it right away. Tell me.
What's the difference between elastic limit and the yield stress?
And what?
And the yield stress, because it seems like they're on the same.
Okay, the difference is if I unloaded at the elastic limit, I will not have any permanent deformation. But in the yield, if I unloaded, you need to go back like this in a line parallel to this linear line, and you're gonna find that your material gonna have a permanent deformation of 0.2% or 0.002. I don't have my calculator on me. Okay. So you understood now, right? Elastic limit, if you unload it at that point, you will not have any permanent deformation. But if you unload it at the yield, you're going to have a permanent deformation of 0.2% for steel and metals. For polymers, we will have a 1% permanent strain. Okay? And again, why don't we, for example, have a reference for our material plastic limit or elastic limit, and we have the yield strength? It's because it's hard to find the plastic limit. It's so hard because what's going on here, it happens quickly. It happens quickly that you can't even track it. Okay? So let's define some things here. So we all agreed that this region is called the elastic region. Beyond that, so let's call this, a minute. So to the left, you have this is the elastic region. You have this thing here we call yielding. And here we have the maximum, this point, we have our maximum, we call it ultimate stress. This is the maximum stress that the material can take. And we can divide it from here to two regions. We have, this is something we call strain hardening. And after that, when the materials start to fail now, that's what we call necking. And that's when you can see an obvious necking in the metals from what you saw in the video. That's when you know, as if it's a warning that, hey, I'm going to break, so you need to leave the building. So we love this kind of material that give us an indication that's going to break. The reason why I speak a lot about like loading and unloading and making sure that the material goes back to its original position, in an example we have in civil engineering, like this, for example. You see how this stadium is going up and down? If we are not sure that this stadium is gonna go back to it, like we need to make sure that this beam behaves in an elastic region, because we don't want any permanent deformation happens here. And I'm 100% sure that all of you have seen like a lot of collapses that happen in stadiums, and people might say, okay, like there were a lot of people, and no, the engineer gonna go to jail because you should predict all this, okay? So that's why it's important to make sure that when we unload, the material goes back to its original position. We don't want the people, when they jump, the beam gonna be like this. And when they jump again, gonna be like this. That's when like the failure gonna happen. And you've seen it a lot. Like you can look at YouTube, like collapses of stadium, and this is bad. And I don't want any of you end up in jail, to be honest. But yeah, this is like the engineer's responsibility. And when that cases happen, everyone starts pointing finger at each other. They will say, okay, the contractor, he stole some rebars, or he didn't use the cross section and they start pointing fingers. So it's not the people's fault. Everything should be designed here. Is that clear? So from what you've seen now, where do you think, what stress we are designing our material for? Are we designing on its ultimate stress, or something here, or something in the linear elastic region? What do you think? Any of you? Linear elastic. And here, what makes sense, we will come to the factor of safety point, which is now I know the yield stress. I know that my yield, which is a well-defined in the stress strain curve, for example, for a material, it's 100. Will I design on the 100, or I will take a factor of safety of 2, for example? And when I take a factor of safety of 2, will I design on 200 or 50? Now it comes the logical part of the factor of safety, which is explained last time. I mean, like, I don't need to show like an equation for factor of safety, but is it obvious that if I told you the yield is 100 and you need to have a factor of safety of 2, will you design it on 200 or 50? I want to see any 200s here? No. Yeah, you're going to jail, and you're going to take me to jail as well. Okay, so, and yeah, returning to the point of factor of safety, because some of you asked, like the book itself, it explained the factor of safety in terms of stresses or loads. Some of you asked me, okay, what about if I want to apply the factor of safety on area? I couldn't find like an expression for like a formula for that. But like if I have to guess, I would say factor of safety, for example, you know that it's capacity over demand, right? And I would say in a form of stress. So, for example, if I want to say a factor of safety, I want to have a factor of safety of 2. So the capacity is 1, as if like this one is a stress over area. And I'm using an area of 20. And this is my capacity. But I want to use 40. So this is demand. So I'm saying 1 over because this is the equation for the stress. Stress is equal force over area. And I'm just like saying force is equal to 1 because they're going to cancel each other anyway. So now, if you have something like this is the capacity, 20, below which is going to break. So I want to increase the area. So you know that if I want to put it now in the right way, I'll put 40, which is I'll take this up, and 20 down, so that I will end up in a factor of safety of 2. Okay? So now if you want to apply a factor of safety, you can't directly put it in that equation. You need to like do like this kind of maneuver. And another thing is, okay, if I want to apply a factor of safety of 2, you can either divide the stress by 2 or multiply the whole area by 2, because I was mistaken by saying multiply the diameter by 2, but no, multiply the whole area by 2, because sometimes we need the area, and after we have the area, we're gonna worry how this shape of the column, for example, look like, if it's circular, rectangle, square, but at least we have the area, we can't go below it. Okay, so now you can say stress equal force over area, and I will carry on this 2 and put it here. So if I also want to apply a factor of safety on like the equation, I either multiply the area by 2 or divide the stress by 2. Does it make sense? Any questions? All good? Okay. So another thing why we call this strain hardening, it is what happens here. We all agree at the yield stress, there is kind of like a breakdown in a molecular level. That's when the molecules start to break and are ready to deform permanently. So what happens more in the strain hardening is it like kind of like rearrangement happens in the like atomic level, that have the material, like make the material harder and like can resist more stresses. As you can see here, like the material here, like after what happened in the yield, the material are actually resisting more stresses, right? Until the ultimate. But if you look what's happening here, I'm actually exaggerating when I draw this stress, like this stress strain. I want to show you, like from the curve, like something like this. As you can see, the linear elastic is barely vertical. But once you go beyond the yield, if I apply a stress in the steel, like a difference in stress is like a very big difference in strain compared to what happened in this linear elastic region. Do you see what's happening? So yeah, at strain hardening and beyond the yield, the material gonna resist more forces, but what's happening with the strain? Like, and even at the top, at like, if I have the laser, at here, the stop, at same stress, like even at a constant stress here, you'll have the material elongating. There is no any increase in stress here, but like there is like an increase in elongation. So with a constant stress, and this is like that's when you know that a failure gonna happen. I'm standing on this slab, and the slab, like I'm not increasing any loads, it's just my weight, and the slab is keep deforming until it's gonna break. So at a constant stress, you have a deformation that's happening without increasing any loads. That's when you know it's gonna break. That's why we don't wanna design anything here. We just stick to this vertical line. And I exaggerated in my notes by drawing it with like a little bit of slope, but like it's barely has a slope. Is that clear? Any questions? Let me tell you something to be like fully honest with you. This is the stress strain curve, but we have something called the true stress strain curve, which is beyond that yield. This is the true, gonna be something like this. Oh. Anyone tells me why this increase? Tell me.
Area decreases.
That's correct. If you notice from the test, the area kept decreasing. So when I divide the same stress over a smaller area, what happens to the whole, the same force over a smaller area, what happens to the stress? It decreases, right? That's why we have higher stress. But again, this is what we call true stress strain, but we don't use it. We just keep with the theoretical because it's hard to track how much the area is decreasing, okay? I still have 2 minutes. Okay. What happened if the material, not all the material have a well-defined yield point. So what if a material has stress strain like this? What should you do? If it's a metal or like aluminum, I know that it's gonna deform. Like we will use something we call offset method, which is a graphical method. We go here by 0.2%, and we make a line that is parallel to this linear line. And whenever this line crosses a point, that's our yield. Okay? When you don't have a well-defined yield stress strain curve, you make an 0.2% here and go in a line parallel to the linear line. Okay? I have a minute, so last thing. But you all gonna help me in that. So you all know when I apply a load until plastic limit, I unload, it's gonna go back to its original position without any increase in, like without any permanent strain. Same thing with the elastic limit. If I applied load until elastic limit, it's gonna go back to 0 with no any strain, permanent strain. But beyond the beyond the yield, so any point here, when I told, the new good notes version is like, yeah. So if I unloaded here, that's the last thing, I promise. If I unloaded here, it doesn't go to 0. It's gonna go in a line parallel to the linear elastic. So this is your permanent deformation. If I told you, if you unloaded at this point, what is the permanent strain? You go in a line parallel to the linear elastic and read this value, and this is your permanent strain. If I told you at fracture, if you unloaded at the fracture, is this your permanent strain or this is your permanent strain? Will you go vertical or will you go inclined? But at fracture, you don't get to unload. It's already broken, right? So at fracture, if I told you what's the strain at the fracture, you don't go parallel. You don't go parallel to this line. You go vertical because it's already broke. But at any point here, if I told you to unload here, you will go back in a line parallel to this line and get me the permanent strain that happened. All good? We're gonna continue in the session. Hello again. So the last thing I explained in the lecture was this 2 slides. So let me go over them quickly. So what I said here, if you have a material that doesn't have a well-defined yield point, what should you do? So the steps is, you will go, like it should be metal. So it's either like, for example, steel or aluminum. You should track, like this gonna be the strain, right? So this point should be 0.002, which is 0.2%. Once you detect this point, okay, go with a line parallel to that linear elastic line. And when this line hits the point, this point is your yield strength, okay? This method we call it offset method, and it's a graphical method. And again, like if you have the same graph, both students might get like different values, but you should all like get somewhere in a range, okay? So this is about the yield strength. And here I was like explaining to you, if I loaded the specimen until the proportional limit and I unloaded, there will be no elongation. The strain gonna be 0. There is no any permanent deformation. Same as if you loaded until the elastic limit, when you unload, there will be no permanent deformation. Here, if I told you, if I loaded until, for example, here, this point, and I unloaded, what is the permanent deformation here? You're gonna make a line parallel to that linear elastic line. And when you hit the point, this point is your strain, and this is the permanent strain that is left in a member after applying this load, for example. Same as here, if I told you after we applied this stress, what is the permanent deformation? So if you apply the stress is gonna go like this, okay? And then when we unload, you're gonna make a line parallel to that linear elastic line. And when you hit that point, this is the permanent strain that's left in a member. And I was talking about, if the material already reached like the fracture, what is the strain at the fracture? It is this strain, right? There is no unloading here because the material or like the specimen already broken. Now, let's differentiate between 2 things now. What is the difference between ductile material and brittle material? As you see from the stress strain curve here, the ductile material gonna elongate, like it gonna elongate and then gonna break. And the brittle material gonna break with no any warning. The warning here is the necking that you guys saw in the video at the beginning of the lecture. So this necking is some sort of like a warning to you, like the elongation, like all this elongation that happened, this is like some sort of a warning, and like what experience such elongation, we call it ductile material. But if a material, after you load and doesn't like experience any like elongation, that's called brittle, like it will break without any warning. So if we want to define them, so the brittle material, so the material that are able to exhibit, so I want to say material that, for example, is or are able to exhibit large deformation before failing. This is what we call ductile material. And the opposite to that is the brittle material, that the material that exhibit little or no yielding before failure. And what we mean with yielding here, like the deformation that you see in the ductile material, okay? So the next thing is something new. We call it Poisson's ratio. And the symbol for the Poisson's ratio is a small v, but it's not like a v. It's like a v with like some sort of like a style. Okay, so you can do your own style, and this is what we call nu. That's how we pronounce it, for example. And the whole point of this is when we apply axial deformation here, a minute. When we apply axial deformation here, you all agree with me that not 100% of the elongation go in the axial. However, I have a percentage of elongation that goes in the lateral direction, which like an explanation to this. When I elongate it this way, this material is gonna increase in length and the diameter gonna decrease, which means that there is also a lateral strain. So we can say that when you cause an axial strain, there is a percentage of this strain goes to the other side, which is like the lateral strain. So not 100% goes in the axial strain. And if I want to give an example to this, if I told you, for example, that I stretched an object, for example, I stretched an object to a strain of 1,000 microstrain. And when you see this micro, you want to multiply by -6, this number by -6, because I don't want to write all these zeros. So multiply 1,000 by times 10 power -6, that's what microstrain mean, okay? And I told you that nu, which is the Poisson's ratio, is 0.3. So this 1,000 is the longitudinal strain. So I will ask you, okay, now what is the lateral strain? So again, the definition for Poisson ratio is a percentage of a longitudinal strain goes to the lateral strain. So if 1,000 goes in the longitudinal strain, so 30% will go to the lateral strain. So if I want to find the lateral strain, I would say 1,000 times 0.3. Okay? So if we want to write like an equation for that, I would say lateral strain is equal to V, or nu, the Poisson's ratio, times the axial strain. And I will give an example in a moment. So the lateral strain is equal to a percentage, which is like nu, a percentage times an axial strain. And this percentage is from 0, if there is no any like axial force or stress, so it starts with 0, until 0.5. From the table that I showed earlier in the class, every material has the modulus of elasticity, and also every material has its own Poisson ratio. So you have a steel, the Poisson's ratio of the steel is 0.3, aluminum is 0.33, and so on. So it's also like a property of a material. So, for example, if I have this red circle, red cylinder, okay, and the original length of that red cylinder was L, okay, and I elongated this using, I applied a force of a P, so therefore the cylinder elongated by delta L. So I have now an elongation. So if you imagine this, you all agree with me, if I applied this force along this cylinder, it's gonna increase in length and the diameter gonna decrease, okay? So now I have this red circle, the original area or original diameter. So it started with this radius, and when I applied that force, it reduced by delta. So now this blue circle is my new circle with like a modified r radius. So the new radius will be r minus this delta. And if I want to find, for example, the lateral strain here, so the lateral strain is delta over r. And delta is like the elongation that happened here. So elongation over the original r, which is the definition of strain. So that's the lateral strain. So lateral strain is the strain that happened in the lateral direction. Longitudinal strain, which is this, the strain that happened in the longitudinal direction, which is delta L over L naught. The elongation that happened, delta L, over the original length, which is L. The lateral strain, the elongation that happened, which is like shortening now in our case, so it's shortened by delta, that's in the numerator, and the denominator is r, which is like the original radius. Okay, so Poisson ratio here is mu equal to, for example, this is the equation, right? So nu here is equal lateral strain over the axial strain. So I want to say lateral strain over longitudinal strain. And there is something we need to add to this equation, a negative here. And this negative is because when we apply a longitudinal strain, it's going to increase in length in the longitudinal strain, and in the lateral direction is going to decrease in length. So that's why we put negative. And the vice versa. Instead, if we applied compression to this, for example, this bar, it's going to decrease in length in the longitudinal. It's going to decrease in length, but the area, like the lateral strain, going to increase. So there will be always be someone greater than the other, or someone increasing and the other one is decreasing. So that's why there is this negative. So this was an example of like a cylinder. So let's talk about if I have a plate like this. So if I have a plate, I have length, I have width, I have thickness, okay? And I applied a force that caused an elongation to this plate. Here is the force, P. I applied this force, and it elongated by delta. I didn't write the delta here, but you should find delta L, which is L final minus L initial. Okay? So now, how many lateral directions do I have? I have a longitudinal direction, which is this L, and I have the first lateral direction, which is in the direction of the W, and I have the second lateral direction, which is in the direction of thickness. So if I want to put it in terms of axes, I have x direction, which is longitudinal now, and I have y direction, which is one of the lateral directions, which is like in the W direction, which is in the width, and then I have a z direction, which is in the thickness direction. So again, the Poisson's ratio equations still holds by saying Poisson's ratio is equal to negative lateral strain over longitudinal strain. So what is the lateral? I can say, I can work with either the W or T. I will show you now. So I will say E in the W direction, which is, for example, delta W over the original W, okay, over the longitudinal strain, which is delta L over L naught, or like the original length. Or I would say negative strain in the thickness direction, which I would say delta T over T naught over E longitudinal, which is delta L or L naught. So the longitudinal is always in the denominator. What in the numerator, it can be either one of the lateral direction, either the width or the thickness. This equation is equal to this equation, and it's all a ratio, and all this ratio is equal to nu, which is a Poisson's ratio. Okay, and I will solve an example in a moment now. Let me explain one last thing, which is the shear strain. When we have a deformation that's parallel to the cross section. So I have now this this bearing, and I will show you a video that explains what's going on here. So this is what we use in earthquakes. So this is something we put under a building to absorb the earthquake force. So this is how it moves. So it moves, like if this is the cross section here, it moves parallel to the cross section. Okay? So this bearing, actually it's having a shear strain. So let's go here, and then this is the bearing. As you can see, when we apply a force like the earthquake force is horizontal. This bearing gonna move like this, right? It's not moving up or down, it's instead moving right and left. Okay, and this angle here, we have this angle. This is what we call shear strain. Okay, so when I apply a force, this force gonna cause this shear strain to happen. So in normal strain, I had the strain was in terms of like elongation and like shortening, but here I have the shear strain in a form of like an angle, okay? And let's agree on something. If I, so this is, for example, the force, and I would say this is the shear stress. So if I have a shear stress like this, and you can tell me if I want to draw a relationship here, shear stress and shear strain, when I increase the shear stress, what's gonna happen here? Do you agree with me that the shear strain gonna increase? So it's like directly proportional. And it's similar to the stress strain though. So it's gonna go like this, okay? And it also has like a proportional limit, like at the end of the linear elastic region, we have a proportional limit, and we call this proportional limit, or the shear at the proportional limit. And as you can see here, we have a linear elastic region, and we have, when we increase the stress, the strain increase. So you notice that I have a slope here. At the stress strain curve, the slope was the modulus of elasticity, but now the slope in the shear stress and the shear strain, what's something we call G, which is the shear modulus. So we had modulus of elasticity, now we have a shear modulus. And if I wanna like do this relationship like what we did in the stress strain, I would say stress is directly proportional to the strain. So I can remove this this relation. I can put constant, and this constant is G times gamma. So the relationship, or like the formula for the shear stress, is equal to gamma times, or like I want to say G times gamma. And this is a shear stress. This is shear strain. And the shear strain here, the units is in radian, okay? Before we had the normal strain, it was inch over inch. Now we have the shear strain in radian, and you all can tell why, because it's an angle, okay? So the G is also like a property of a material, and we also can find them in the table that had the modulus of elasticity. So we had the G. It is called modulus of rigidity, and we can call it shear modulus. So it has multiple names, and you can see the units for that is the stress units, similar to modulus of elasticity. So if I want to define the G, which is the shear modulus, I can say is a measure of material ability to resist transverse deformation. Or I can say lateral deformation, okay? And the G, either you get it from the table or it has an equation, and this equation for G is equal to modulus of elasticity, which is E, to 1 plus Poisson's ratio. So we can later in the semester, we can go through how we can like get this equation, but for now, you can either get the G from the table, like it's like will be given in the question, or you can use this equation to get the G. So in the booklet, we have this example, and this is the last thing. So I had a bar with a length of 12, width of 1 inch, and a thickness of 0.5 inch. And the question, we told you that this rubber block is pulled so that it deforms by 1.5 inch in the x direction. So in the x direction, which is the longitudinal direction, and longitudinal means like the length, which is like the largest length. So I would say in the longitudinal direction, it deformed by 1.5 inch. So the delta in the x direction is 1.5 inches, okay? So the questions ask you, how much does it deform in the z direction? So what is like the delta in the z direction if the Poisson's ratio is 0.5. Okay, so you would simply write the formula of Poisson's ratio. So Poisson's ratio is equal to negative lateral strain. So lateral strain here, I have either the lateral in z direction or in y direction. Now I'm interested in the sigma z, which is in this direction. So I have two lateral, either this lateral or that lateral. And this is the longitudinal direction, which is like the largest length. So I would say E lat over epsilon longitudinal. And the epsilon lat is equal to delta z over z, which is like the original length in the z direction. What was the original length in the direction? It was 1 inch. I will write here 1 inch. Okay? In longitudinal direction, I have delta x over 12 inch, which is like delta x over L. So instead of delta x, I can write 1.5 inch. And the whole thing is equal to 0.5. Again, plug it in your calculator, and you will get delta z is equal to negative 0.0625 inch. And the reason why it is negative here, because when we apply elongation in the x direction, you all agree with me that the width is gonna decrease and the lateral gonna decrease. That's why when we get the delta z, like in this z direction, it decreased, right? And if we are asked to get the delta in the y direction, we also expect to get a negative delta value. And that's all, and I will see you in class. Thank you.